Good evening. Ooh, that's up nice and loud. Welcome back to the Saddlebrook Science Cafe series. My name is Erin Deely, Director of Recruitment and Engagement at the College of Science, and we're delighted to be back for the second in this series. I would like to apologize for not having our materials out and ready for you as we usually do at the beginning when the doors first open. I can assure you everything is out now. In addition, many folks brought it to our attention. We had a typo in our first run of the brochure. So for the December talk, it says Thursday, December 5th, and it's actually Tuesday, December 5th. When we send out the reminder email message to everyone, it is corrected. It's corrected in the calendar. It's corrected as far as a saddlebag, and the flyers that we distribute here. So thank you for bringing that to our attention, and apologize for the confusion. In large part, our presenter actually had to be at a conference, so we had to switch around that time. But typically it's the same time of the month, same week, and same evening. So by a show of hands, anybody here for the last talk? Great, and those of you that are new, welcome to the second in the series. Our series is from the Earth's core to the clouds, and we started with the first lecture in the deep Earth, the core. And if you didn't get a chance to see that presentation, when you pick up one of these brochures, our website for Science Cafe series literally has the podcast or the video. And right now, this will be simulcast as well and available on that same website. So some folks like to revisit that or see it for the first time. I'd also like to mention this is one in a series of 4 science cafes provided by the College of Science in partnership with our community organizations like the DesertView Performing Arts Center, also at downtown Magpie's Pizza, Tumamook Hill, which is right next to A Mountain. It's a 100-year-old desert laboratory owned and managed by the U of A, as well as Borderlands Brewing, which actually is a community center, has great beer, doesn't hurt. And actually that's where we showcase our PhD candidates that also want an opportunity to bring their research to the community and have a chance to communicate science as part of their PhD program. So if you enjoy this one, you might enjoy visiting some of those other venues. And as I mentioned, this brochure lists all of those venues, times, titles, and themes. And of course, we'd like to thank the DesertView Performing Arts Center staff. Makes it possible for us to be here. And of course, there's no money exchange. This is a pure community partnership. We're delighted to be up here. And as you know, we bring U of A faculty to give talks here at Saddlebrook Science Cafe. And this year we partnered with the Geosciences Department and with a great series. And I just wanted to mention, in addition to our regular materials and brochures of our outreach facilities like Biosphere 2, Flandreau Science Center, Tumamook Hill, the Laboratory of Tree Ring Research, and Mount Lemmon Sky Center. We also have materials from the Geosciences Department if you want to learn more about how to get involved or support that department. They do amazing work. Our own dean, Joaquin Ruiz, is a graduate, a PhD of geosciences. So, and almost every astronaut out there was a geoscientist at some point, or continues to be. We will have evaluations available for you. They're out on the table outside with some pencils, and this is great feedback to our speakers. We definitely provide them your insight and suggestions and overall evaluation. At the end of those forms, or at the bottom of the form, is a place to put your email address. We will send you the email, which is the reminder the month before the talk, and then any other free offerings from the College of Science. But we certainly don't fill in your inbox, and we're never going to ask you for money or try to sell you anything. So in addition to providing that email address, if you would like to give us suggestions about themes or topics that you're interested in, this series came about because of feedback from this audience. They wanted to learn more about geosciences, so voila, here we are. All right, without further ado, let me just introduce our speaker tonight. Barbara received her master's in science from the University of Pavia, Italy. She has a PhD from the Free University of Amsterdam in the Netherlands, 2002, and postdoc at the University of Wyoming, an associate professor at the University of Arizona, and has just now transitioned to a full professor since 2016. That alone deserves a round of applause. Since 2010, Barbara has studied orogenic processes, which include the processes responsible for the formation of mountains on Earth and possibly other planets, due to the convergent movement of lithospheric plates driven by mantle, convection, and other processes. This will be explained. Barbara spent a lot of time in remote places such as the Andes, Tibet, Nepal, Pamir, and sometimes spends several months a year sleeping in a tent. Kind of explains her slim physique. She states that therefore she has a deep appreciation for nice bathrooms, showers, and comfortable beds. She loves the opera, hiking, skiing, but most of all, horse riding, in particular jumping. We look forward to hearing her talk. And I've just mentioned, just after her presentation, we will work the crowd with microphones and ask that you pose your question and then pass the microphone back to us so that we can get full representation. And depending on how much time remains, we'll invite folks up for a bit of time to actually ask Barbara some questions one-on-one. So, Barbara Carapa.
Thank you for the introduction. I'm actually excited tonight to be here and share my science with you and talk about what we do, some of the science we do in the College of Science, which is very exciting. I have been working on mountains and mountain building, so processes forming mountains for quite a long time since my PhD, and I'm very passionate about mountains. So this is what I'm going to talk about today. And I'm going to concentrate on the scientific aspect of mountains and why they're important, but I will also highlight some other aspects of why mountains are important for society and biology and evolution and climate. So let's start by looking at why are mountains important. We probably all appreciate mountains because they're beautiful to begin with. So as humans, we do appreciate beauty in nature, but they also provide fresh water, food, and energy for a lot of people, especially the most populated areas on the planet are actually receiving water, fresh water from mountains like the Himalayas. They also deeply affect climate and biodiversity, and we're going to look at some examples of that. And they also have cultural significance, like in the Himalayas and Tibet and Nepal. And I'm going to briefly show some pictures of these places and give some examples of that. So obviously mountains are not just scientifically important for geologists, but they're also they have a society significance. So where are the highest mountains on Earth, and what is the highest topography on our planet located in, and what are those mountains associated with? So that's where we're going to get into a little bit of geology. And again, if you have questions at the end and it's a little too technical, I'm happy to just step back and give you some more feedback or information on how actually the whole system works. But some of the highest mountains on our planet are concentrated in Asia, and the Himalaya, and most of you probably know Mount Everest is the highest mountain on our planet. But also the Andes are form some of the highest mountains on the planet, especially in a different kind of tectonic setting. So the highest mountains on the planet are associated with convergent margins, so where you have plates that they're coming together and pushing each other, pushing against each other. And so that's what we call convergence between plates. And in the case of the Himalayas and also the Alps, see if it's actually not working. Basically, you have two continental plates coming together and colliding with each other, and that's what we call collision. In the case of the Andes in South America, you have an oceanic plate subducting under a continental plate. So they're still converging, meaning they're coming together, but there is actually an oceanic plate subducting under a continental plate. So there is no actual collision, it's just convergence. And the highest mountains are concentrated along those two boundaries. So the triangles are basically examples of places where I've done active research in the past, and I'm still working today. So I've been working a lot in the Alps during my PhD and postdoc. I'm currently working the Himalayas and the Pamir, which is the western continuation of Tibet, and the Himalayas to the west. The Andes are an area of active research, and the North American Cordillera. So these are just photos that I've taken during my trips to the Himalayas when I was doing fieldwork a few years ago. just to show you how the topography is extreme in these places. So Mount Everest is over 8,800 meter high and is exposing very deep crustal rocks, which are now at the surface. Actually, the top of Mount Everest is made of limestone and marine limestone, which are now at over 8,000 meter elevation. Mount Kailas is another big mountain that is in basically the southern part of the Tibetan Plateau. So you're actually inside Tibet, and is made of a very different type of rocks. They're sedimentary rocks, and you can actually see the horizontal layers to the right where Mount Kailas is. So the mountains have different shapes. They're made of different rocks, and but they're all basically uplifted to high elevation to tectonic processes, meaning plates again coming together and smashing against each other in this case. And then one key element of exposing and creating topography is erosion, which we're going to talk about. Mountains have also, so as I said, in particular in the Himalayas, these big mountains are sacred. So the Hindus and the Buddhists walk around, for example, Mount Kailas, which is to the right, in a clockwise direction, and the giants and Bompas people walk counterclockwise around the mountain. So actually you can't go to the top of Mount Kailas because it's a sacred place. And so we actually, in order to study Mount Kailas and the processes involved in the formation of this big mountain, we actually had to go around and in different, peaks around nearby, but not quite at the top of Mount Kailas. So this is a movie that hopefully is going to work to just show you the difference between continent-continent collision, which is a process that formed the Himalaya, versus ocean subduction under a continent, which is what formed the Andes. So we're going to look at continent-continent collision and see India is coming in and is smashing against Asia. So it's coming in from the south towards the north. You're basically having two continental plates that are going to collide with each other, and one continental plate is going underneath the other continental plate. In this particular case, you have India going underneath Asia, and then eventually you have processes like slab breakoff or lamination, where you're actually getting rid of some of the lithosphere. I'm going to play this again so where you can see that India is coming in from the south very fast, colliding with Asia and creating the Himalayas. Now, now we know there is actually research in our department on the timing of collision. We know that by 60 MA and earlier, actually, the collision had happened. So these movies are obviously not up to date, but they're going to give you at least a good idea on what is going on in terms of what is creating basically the big mountains that we see today. Now, in the case of the Andes, you're also seeing really big topography and big mountains. The highest mountains in the Andes is Mount Aconcagua, which is over almost 7,000 meter high. It is in a different tectonic setting, meaning you're looking again at an oceanic plate under a continental plate. So there is no active collision, but the plates are coming together and there is convergence. The rocks exposed in the Andes are mostly volcanic. There are not that many metamorphic, actually high-grade metamorphic rocks in the Andes because there is no collision, and there is the depth of erosion is not as deep as in the Himalayas. However, they form these big, amazing peaks, and this is also the place where Charles Darwin did his expedition in 1835 on board of the Beagle, and it crossed actually the Andes right here where the Aconcagua Mountains are. So this is a movie that shows the processes related to the formation of the Andes and places similar to the Andes, like the North American Cordillera. Where, as I said, you have a convergent plate margin, but you have an oceanic plate subducting under a continental plate, and your oceanic plate is the Nazca plate under the South American plate. So you have a subducting oceanic lithosphere, which is going to, as it goes down into the mantle, is going to dehydrate and is going to create magmatism, and so you have an arc. And a lot of the high mountains in the Andes are made of volcanoes. And you have a lot of material that gets scraped off the subducting plate that gets piled up in front of the subducting plate, and that's the accretionary wedge that actually was represented in this little movie. So I'm playing it again just in case you miss some details. But so processes are similar in the sense, again, that you have those plates coming together, but the plates are different. So for the Andes, you have ocean, continent, and for the Himalayas, you have continent, continent. Okay. So mountain building and climate. So mountains are affecting climate in different ways. One fundamental way that they're actually affecting global atmospheric circulation is that they're forming big topographic blocks to atmospheric circulation. So think about the Himalayas. They're really high, they're also very long, and there's Tibet behind it. And so when precipitation comes in from the south, it basically is going to meet this huge barrier. We call that an orographic barrier, and so it's going to dump all the precipitation right there in the front of the mountain. And so that's what is basically causing the Indian monsoon in the case of the Himalayas. So basically the interaction of big topographic features in the front, also the presence of a big plateau on the backside is blocking precipitation and creating the Asian monsoon. So this is a precipitation map of the Himalaya and Tibet, where you can see that the blue colors are area of high precipitation, and the red is basically Tibet, where you have almost zero precipitation. You can see how extreme the contrast is. Basically all of the precipitation is concentrated in the frontal part of the Himalayas, and there is basically nothing getting into Tibet. So as you cross the Himalayas, when you're in Tibet, you're basically in a high desert environment, whereas in the Himalayas and the south, like Bhutan and Nepal and India, it's a very different type of environment. So obviously understanding when these big mountains were uplifted and creating this big orographic barrier is important for our understanding of long-term climate, but also biodiversity and also the processes that are related to the interaction between tectonics and climate. So this is just an example of how the strength, basically, it is a photo of how much water actually the Asian monsoon brings to the Himalayas, which is again related to precipitation coming from the south, meeting the Himalayas and the Tibetan Plateau, and basically releasing all the precipitation right in the front side of the Himalayas. Now, mountain building and mountains are also fundamental. They also exert a fundamental control on faunal migration, and so flora and fauna. This is a paper that came out recently showing that basically there is a big spike in dispersal of species at about the time of collision between India and Asia. So I don't expect you to understand these graphs. It's just showing basically the numbers, so that the histograms to the right, where my little mouse is, just an example, is showing basically a spike of when the species are the dispersal events of different kind of species in India. And those are different kind of animals that we see, and also the appearance of specific species in time is basically telling us that when India gets close to Asia, and by let's say 55 MA, you have actually contact between India and Asia, you actually start seeing dispersion of different species and faunal exchange between the two continents. So obviously, plate tectonics and the formation of mountains and through land creation of land bridges and the contact between two big land masses is affecting deeply not just geology, but also evolution and fauna and flora dispersal. So the questions that I like to ask, or some of the questions that I concentrate on in my career, are how and when do major mountains form? Because in order to understand all this feedback between climate and tectonics and eventually also biology, we need to understand the processes creating mountains, but also the timing, which is fundamental. And eventually, what is the role of climate? Of course, we're talking about deep time here on tectonics, and possibly vice versa. What is the role of tectonics on climate? So what is orogeny? So as geologists, we often use jargon or words that maybe most people don't understand. So I'm going to go through some of the key language that I'm going to use in my talk. One of the key sort of processes that we always talk about when we talk about mountain building is orogeny. And orogeny is nothing else than all of the processes involved in forming mountain. We just call it orogeny. There's also a really nice wine actually called orogeny, which I found and I kind of like. So I put it there. So if you don't remember what orogeny is, at least maybe if you find the wine, you will get reminded. So in order to actually get orogeny and mountain building, you actually have to have plate tectonics going on, right? Plate tectonics is the unifying theory in earth sciences, which basically describes how plates on the surface, or lithospheric plates, which are hundreds of kilometers thick at the top of the earth, are floating on top of the asthenosphere. Okay, so lithospheric plates are more rigid and they're floating on top, and not really floating, but they're moving on top of a asthenosphere, which is more fluid. It's not really fluid, but is less rigid than the lithosphere. So basically, this is what it looks like, in a cracked like Earth, where you have different plates moving around on a asthenosphere. And so as we talked about continent-continent collision, for the Himalayas, you have two continental lithospheric plates coming together and colliding with each other. In case of the Andes, you have an oceanic plate going underneath a continental plate. Those processes are basically going to create a lot of stresses and deformation right where the two plates come together, and they're going to form big mountains. But so why are mountains high? Why do we actually have high topography on our planet to begin with? And that's nothing else than the Archimedes principle, which I'm sure everyone actually knows. Right, that's why both float. And this is a nice, let's see if this is actually going to work, maybe not. Let's see. No, it's not working. But it's basically saying that in Archimedes principle, if you have a body that you put in water, that body is going to be lifted up by a buoyancy force, which is proportional to the weight of the water that is displaced by that body. Okay, so basically that's Archimedes principle. In geology, we use Archimedes principle, and we actually see the effect of Archimedes principle in terms of, if you're actually looking at, for example, the Himalayas, every time you see a big mountain, you should expect to see underneath a big root. Okay, so the root of a big mountain is at least 7 times higher than the height of your mountain. And that's just based on Archimedes principle. So every time you have a big mountain, you have a big thickness underneath the mountain that is sustaining that topography. We call this area isostasy, meaning that the changes in height of mountains is a function of thickness. And so we know that, we can measure that, so we know that that's basically what most of topography on the planet is sustained by, is by isostasy, which is a basic principle. So how do we actually create mountains? So we know now, we understand how they actually are lifted up, but how do we actually form them to begin with? So as you might imagine, when you have two plates, like in the case of the Himalayas, that are coming together and they're smashing against each other, is like having two trains colliding, right? And so as the trains collide in the middle of it, you're going to have a lot of deformation. And that's basically where you form your mountains. So we call this crustal thickening by basically shortening, by basically pushing those two plates together. That's kind of the basic idea on how you form mountains, especially in a collisional type environment like the Himalayas. But there are other models out there that suggest that actually it is not just all about the forces that are they're taking place when you have two plates colliding. Another way of uplifting, the surface and creating mountains is by basically moving material from underneath, from really deep in the lithosphere, all the way to the surface, and that's called lower crustal or channel flow or lower crustal flow, where you basically have the lower crust flowing underneath the surface and eventually extruding in the frontal part of the orogenic belt. So if this model is correct, and if there are places on the planet where you actually see these kind of processes, then you don't necessarily need to have a lot of shortening. You can just have uplift without having a lot of shortening at the surface. Now, this model was actually created in the Himalayas, And one place where people have suggested that this model, this situation is going on, is Mount Everest. So we're going to actually look at some data testing these two models and see whether or not it's actually working. So another way of uplifting the surface of the Earth is by removing some of the lithosphere from underneath. So again, if you think about Archimedes' principle or an iceberg, if you remove part of the iceberg underneath, you're going to have a rebound effect, and the surface is going to go up as you remove that part of, the keel of your iceberg. And it's the same for mountains. If you're actually removing part of the bottom of your mountain, the mountain is going to rise up due to isostatic rebound. So it's going to readjust due to that removal. And this kind of process has been suggested to have taken place in different places, but specifically in the Andes. So we're going to actually get back to this and test this model in the Andes and see if that's actually what's going on. So we're going to start with Tibet, and I'm going to just show you a few examples, a few photos of our fieldwork in Tibet, and then eventually some of the data that we came up with, and test some of the models and see how actually mountain building is taking place in this part of the planet. So our journeys to Tibet, actually we took several field trips. I've been to Tibet now 3 times, and you always have to fly to Lhasa from Beijing. So this is the Potala Palace in Lhasa. And you get to Lhasa is very high elevation. Elevation is almost, it's over 4,000 meters high. So you go from sea level to over 4,000 meters. So you have to stay there for a few days to kind of just, catch your breath and, figure out where you are. And it takes a while, so depending on how you adjust to elevation. So we usually spend about 4 or 5 days in Lhasa, get our pyramids, and then continue to into Tibet and the Himalayas. So these are mostly our students getting ready for our fieldwork in Tibet. So in Lhasa, usually we store a lot of camping gears. When we do fieldwork in this part of the world is pretty basic. So we're going to cook. We have all sort of cooking gears, we're bringing food, and we're just cooking our own things. And so we have pots and pans and all sorts of things. Food is pretty basic, but it's keeping us alive, and so that's all that matters. Usually you lose a lot of weight when you're in Tibet, so what I usually do, I eat a lot before going out there, and then I'm fine. So that's the fun part about it. So this is basically what we did this particular trip in 2015. We started from Lhasa, then we basically drove westward along the suture zone, which is where the Indus Yarlung River flows, and then we veer down south towards Mount Everest. So you can actually get to Mount Everest from both the Tibetan side or the Nepal side from the north, from the south going northward. And this is coming in from the Tibetan side. And this is a photo of the high Himalayas coming in from the north. So we're actually looking south towards Tibet. So here is, we got to the Rambuk Valley, where is basically the valley that leads to Tibet, to Mount Everest. This is Mount Everest from the Tibetan side. There is a beautiful monastery here, and you just basically sleep right here. There's a little hotel where people stay. There are not that many people actually in this part of the world, although I did find some Italians. You always find them they're always where I am. It's kind of interesting. There was no one, but there were Italians over there. So we actually have special permits when we work in Tibet. We do need special permits, especially for collecting rocks and samples. So this is just, a photo of our stay. And we stayed basically in this place for about 4 days when we were there, the first time around. So a lot of people actually ask me what I do when I'm not in the office, because I spend a lot of time outside doing fieldwork, and a lot of my colleagues sometimes they joke saying, "Oh, you're on climbing mountains and you're having fun. It's vacation," but it's actually not vacation at all. Especially when you have to climb a 6,000 meter high mountain. I'm still actually working, so I'm out there working, sleeping in a tent, carrying my own food, not very much, and collecting samples. So what I actually do is collect samples of metamorphic rocks, granites, or sedimentary rocks, which I then bring back to the lab and analyze with all sorts of different techniques. That takes a lot of effort and time. And this is just an example of a trip that we took up a high mountain, collecting different samples of different elevation for eventually doing thermochronological analysis, which I'm going to explain next. Okay, so to go back to the model and why we're doing this is just an example of the things we do. Of course, we've been working there for a long time, so there's a lot of science coming out of this. But just to, I had to select something that was sort of contained and to the point. So one of the main model that is used to explain Mount Everest is that, as I said before, is that there is actually a channel of lower crust coming in from underneath Tibet and extruding right in front of Mount Everest. Okay, so this is the channel flow model that I was talking about. Now, for this model to work, you actually need to have a lot of erosion in the frontal part of the Himalayas to allow for a lot of material to be removed and to keep the channel basically flowing in, right? In order to actually create that gradient and bring material in and getting extruded, you need a lot of erosion in the frontal part. So a key component of this model, or the predictions of this model, is that you need to have a lot of erosion that is climate driven in the frontal part of the Himalayas and has to be going on today. Okay, so the good thing about science is that science to be called science, we need to have predictions. We have an idea which we call a hypothesis, then we make predictions, and then we test the predictions, and if the data don't test the predictions, then the hypothesis doesn't work, right? And we go back to the whiteboard and we start with another idea. So the good thing about this model or hypothesis is that it makes very testable predictions that we can actually test with data. So the implications of this model is that climate is actually controlling tectonics by eroding a lot of material and bringing in material from deep into from the interior of Tibet outside into the frontal part of the Himalayas. Now, the role of climate on tectonics and vice versa is kind of a topic of debate. So there are a lot of different ideas out there. These are just examples of two papers that came out in Nature in the last, let's say, 5 to 10 years, saying basically opposite things. One suggesting that there is a decoupling of erosion and precipitation in the Himalayas, meaning that climate is not really connected, tectonics and climate are not coupled. And the other suggesting that actually climate is driven tectonics. So there's an ongoing debate on the role of climate on tectonics and vice versa, and on the interaction of the two. And so understanding these problems is actually significant. So how do we date orogeny, or the processes responsible for the formation of big mountains? Every time you have a lot of deformation, especially in collisional mountain belts like the Himalayas, you're creating topography and you have a lot of erosion through surface processes. So when you remove material from the surface through erosion, you're actually going to cool rocks that were once deep into the interior of the earth to the surface. So if we can find a way to date that cooling through time, then we can actually date the process of erosion. And that's basically what I do. I use techniques that allow me to date erosion, and those techniques are called thermochronology, and I'm going to explain that in a second. So thermochronology is basically a tool that dates erosion. So it's a technique that you apply to different minerals, and is based on the natural decay of a certain isotope into an unstable isotope into a stable isotope. So it's based on radiogenic decay. Radioactive atoms, they decay from an unstable state to a stable state. And basically that process of decay is a function of temperature and time. So we can actually use that process to derive time, and so age, and then we can use that as a proxy for erosion. So when we apply these techniques to different minerals, this is just an example of an apatite, which is a mineral that is commonly found in metamorphic rocks and intrusive rocks. We actually get an age in million years, which can be used as as a proxy for the age of erosion, which is in itself a proxy for the timing and magnitude of tectonics and surface processes. So that's how we actually get to understanding tectonics. The technique in particular that I use often, and that's one of the lab that I manage at the U of A in the Department of Geoscience, is called fission track dating, which is based on the spontaneous fission of uranium-238, which is an unstable parent, into a stable daughter. In this case, the daughter is, they're actually tracks within a crystal. So these little guys, black guys, those are tracks that are basically left behind by that spontaneous fission of uranium-238. So this process, again, is time temperature dependent, so we can actually derive time from this particular technique. So I'm going to actually jump into the data, and again, this is a complicated figure, and I'm not expecting you to understand that. But again, if you remember what I said about the predictions, the channel flow model predicts that you need to have a lot of erosion going on in the frontal part of the Himalayas, where the channel is coming out, and that erosion has to be going on today. Okay, so where the channel is coming out is actually Mount Everest. Now, we have dated these rocks using thermochronology, and we found that the age of exhumation or erosion of those rocks is about 16 million years ago. And that erosion, that age, also suggests through modeling, which I'm not going to show you right now, you kind of have to believe me, that that event of exhumation was very rapid and very quick. And after 60 million years ago, not much erosion has taken place at Mount Everest. And so the predictions and the data are actually not supporting the channel flow model, but just suggest that actually Mount Everest and the exhumation of Mount Everest occurred through a normal fault, which is the SCD. But also, when we look, so these are basically figures showing ages on the x-axis and elevation on the y-axis. So those are ages of different rocks that were samples at different elevation near Mount Everest. Obviously, we didn't climb on Mount Everest. We actually couldn't, and I couldn't have done that even if I had permits. So we actually climbed a little 6,000 meter high mountains just nearby and collected samples at different elevation. And so we actually got ages of these samples, showing that the fact that all these ages are the same at different elevations suggests that exhumation or erosion was very rapid and happening at the same time. Now, these are ages coming off. So we call this a probability density plot. So those are PDFs of ages where you have ages, again, on the x-axis, and then on the y-axis is basically a density function. Okay, so the height of the peak. So if you have a really long peak, that suggests that a lot of your ages are within that particular age. And so those ages are ages coming off rivers draining the Mount Everest region. So we collected actually sand coming off the river. So one way of actually dating erosion of a mountain that you cannot climb is to take a sample of sand coming off the mountain and letting the river climb the mountain for you. And that's basically what I did. I collected a sample of sand that is coming from Mount Everest, and I got ages coming from Mount Everest itself, all showing 16 MA. So it's the same age spectra that we see for the ages that we actually collect in situ. And so the entire data set supports very fast exhumation at 16. But we also did some thermal modeling suggesting that basically after 16, erosion stopped. And so the scenario that we came up with based on our data and some modeling exercises is that the Tibetan Plateau was actually was extending further to the south than it is today. So it was not just stopping at Mount Everest, it was actually coming further to the south into Nepal at about 16 MA. And then after 16, erosion due to headwater erosion, river and glaciers actually created the topography that we see today. So erosion migrated northward due to headward erosion of rivers. And what we see today in Mount Everest in terms of topography is the result of that northward migration of erosion. But the uplift history of the whole Everest area is associated with an event of uplift which extended further to the south than Mount Everest itself. So the implication of this study, which was published in Geology in 2016, is that tectonics actually is the major control on climate. So it's basically what controls where orographic barriers are. And then eventually when you stopped that engine of tectonics, then you can have erosion taking over and basically removing a lot of material and creating the modern topography. So in the Pliocene, let's say in the last 5 million years, rivers and glaciers have cut back into the Tibetan Plateau and have created the topography that we see today. So overall, this study does not support the channel flow model, but does support the model that Tibet and the Himalayas are related to crustal thickening associated with shortening, and that Tibet actually was wider and bigger than what we see today, which has actually big implications. So briefly on the Andes, I don't want to take too much time. So the Andes are a different system. Again, here is a cross-section through the Andes where you have oceanic lithosphere under continental lithosphere, so convergent plates, but different type of plates. The Andes, like the Himalayas, they exert a huge control on climate. This is a map of precipitation along the Andes. The red shows basically 0 precipitation, and the blue is over 4 millimeter of precipitation. And you see that along strike, you have a big gradient and changes in precipitation, depending on where basically the winds and precipitation comes in, okay? So north of 30, you're actually looking at precipitation coming from the east, and south of 30, precipitation comes from the west. But because they're so long, they're also affecting global ocean circulation. One of the major currents that is affected by the Andes is the Humboldt Current, which is the largest upwelling current on the planet, which brings cold water up to the surface and affects biodiversity and brings a lot of nutrients to the surface of the ocean. So obviously understanding when the Andes formed, this big barrier to both oceanic and atmospheric circulation is important for understanding a lot of different things, not just tectonics and plate tectonics, but also climate and biology. So this is how the Andes look like when you're up high in the big high mountains. It's similar to Tibet in the sense that they're very dry. They have relatively low relief inside. They're internally drained, so there are no rivers going out of the plateau region, which is the central part of the Andes. And you have peaks that are over 6,000 meters high. So popular model for the formation of the Andes is that most of the uplift in the Andes occurred in the last 10 million years. And that was related to removal of part of the root of the Andes and uplift due to isostatic rebound. So obviously, understanding when the Andes came up is important, as I said, because there's a lot of implications on how, the relationships with climate, but also faunal and floral distribution. So I'm just going to show you a couple of pictures about one of our last expeditions that we did in the region. This is an expedition that we did in 2015, which was funded by National Geographic, and we were actually looking at the uplift history of the Aconcagua mountain, which is right at about 34 degrees south. And hopefully this video is going to work. So this is just a view of the old, basically, high Andes from near the Aconcagua mountain as a 360 view of the mountains, and you can see that it's very dry. There is some snow. There is some snow, permanent snow, but there are basically no glaciers in the Andes, even though they're very high. They're just located in a dry zone. There is not enough precipitation. Most of the rocks that you see here are volcanics and sedimentary, so there is not a lot of metamorphic deep crustal rocks. So this is just a nice view of the old Andes, just from a place that we were working in. So again, as you can see, in order to work in these places, you actually need to climb up mountains and collect samples from the top. So this is another video that shows that fieldwork is not always so pleasant. We were actually trying to collect samples and from a high location, a big high mountain near Aconcagua, which is called Mercedario. And we basically got caught into a big storm and we were trapped in a tent for 4 days. And I literally thought I was not going to come out of this because we basically lost trail. There was no trail, but we didn't know where we were going. And this is just a video that I took once we were down. We were actually camping up here, and I felt that I was alive and I was going to make it. But I thought that, yeah, it was pretty close. Although it's not a bad way to go. You know, you're doing field work in a nice place, and so that's. I was looking at the silver lining there. This is a video of, you know, again, when I acknowledge, my colleagues obviously are always acknowledging my talks, but I want to acknowledge the real field assistant here of our fieldwork. So when we do fieldwork in these places, we actually do need animals to carry our food, our tent in, and then they come and pick us up and they carry all the rocks down. So this is just an example of the donkeys came to rescue us at the end of our week camping out in the middle of nowhere, and we had a ton of rocks that they had to take down, and we wouldn't have been able to do it without them. And I'm always amazed how chill they are, and you look at them and you feel like everything is going to be fine. This is Peter DeSalle, another professor in the Department of Geosciences. We were doing fieldwork together. We were lucky we were married, so we can actually spend a lot of time together out there. So, but basically, this is our camp. There is not much going on here, you know. So you really have to love geology and the rocks, and we do. So we're very excited to spend time out here. But again, this is the end of our expedition. So this is basically what we came up with, just to kind of get to the conclusion of what's going on in the Andes. So one model is that everything is happening at 10. It's coming up because you have removal of part of the lithosphere and isostatic rebound. And what we came up with, based on a lot of data that we have collected over the years, is that actually the Andes have grown to elevation that we see today since the Paleocene, so about 50 million years ago. And uplift has migrated from the west to the east, not in a kind of a steady way, but by jumping. And the jumps that you see here, by looking at basically how the elevation and the mountains are forming, are related to basically how thrust faults or big structures are actually breaking the surface due to a lot of different processes that are connected with basically the subducting plate and how basically stresses accumulate in the upper crust. But the bottom line here is that the Andes didn't come up all at once at 10. They didn't come up due to a big drop off of the lithosphere. They came up since the Paleocene, so since 50 million years ago, and uplift has migrated progressively from the west to the east. So the implications of this are actually big, not just for geology, but because, for example, if we look at the Amazon, which is one of the places where you have the biggest biodiversity on the planet, the models that exist today for biologists are all based on having the Andes coming up pretty late, at about 10. So if we actually start the clock back in 50, that has huge implications on how all these species that we see today have basically diverted, you know, when you start that basically diversion of species. And so as a lot of implications for fauna and flora. And so for biology. This is basically what we came at the end of our effort in the Andes. All the research that we have done as a group in our department and involving also people outside of our department was resulted in this big volume that was published by the Geological Society of America in 2015, which contains more than 20 chapters on the Andes. So that was a big group effort. And that's something that I want to stress, is that all this research wouldn't have been possible without, obviously, the help of colleagues, especially within my department, which is very strong in tectonics. And the fun part about our department is that we work together on these projects, and so that makes science much more interesting. And with that, I just want to acknowledge our sponsor, NSF, National Science Foundation, and National Geographic, and some funding from ExxonMobil. Thank you.
So as I mentioned before, first I want to make an announcement. Someone seemed to have lost a ring in the foyer. So if someone, it's a woman's ring, please visit with us afterwards. If you check your hands and something's missing, it could be that it was here prior. We'll have you come down just after. But let's take some questions. Samantha has a microphone. I have one on this side. We'll do our best. Any questions for our speaker? Oh, way in the back, of course. Get my exercise.
Could you please try to explain how you determine the deterioration with this radioactive stuff for me one more time? Because
Yeah, it is actually pretty complicated. I teach a class that takes an entire semester on this, so I'm not surprised you don't get it just by one slide that lasts like 20 seconds. So fission track in particular, or in general, I should step back and say that every time you're looking at thermochronology, which again is a technique that dates cooling of minerals through a certain closure temperature, that's based on a radioactive decay of a parent isotope into a stable daughter isotope. So you start from an unstable parent and you end up to a stable daughter. And that reaction, which is based on radioactive decay, is temperature and time dependent. So depending on the technique that you're looking at, different techniques, in particular fission track, are sensitive to temperatures at about 120 degrees C, Celsius. So that means that the clock starts at 120 degrees C. So you're starting accumulating tracks, which is the daughter product of your radioactive decay, as you cross that temperature. Now, temperature, if you think about temperature in the crust, you can translate temperature into depth, right? As you go down at depth, temperature increases. As you come up, temperature decreases. So the way to decrease temperature, and so to cool a mineral that was, let's say, sitting at 120 or 200 degrees C, is by removing material from the surface through erosion. So if you do that, you're basically cooling your mineral, which was originally deep down, and it's going to cool and eventually get to the surface by basically removing the cap, right, of the mountain. And so that's basically what we are looking at. We are dating minerals that were once deeper in the crust. They were exhumed through erosion, and we're basically dating the time when that particular mineral crossed the 120 degrees C temperature in this particular case. So we know that that is about 4 kilometers deep if you're using a normal geothermal gradient of 30 degrees C per kilometer. And so you then can calculate not just the timing of erosion, but also the rate of erosion. Does that make sense?
Can you explain to us how our own local mountains were formed and why they're in short segments all stretched out throughout the valley?
For the Andes?
No, for the Catalinas and our local mountains in Arizona.
Oh, in Arizona. So maybe the Catalinas is maybe a good example now. Yeah. So Arizona, and so the mountains that we see in Arizona are mostly formed by extension. So it's a different process. You're actually not looking at plates converging, but they're actually, we are stretching the crust by extending it. So the Mount Lemmon and the Catalinas is a classic example of a big normal fault, which we call a detachment fault, where you have actually basically a big low angle fault that is bringing up rocks from deep in the crust to the surface. So you have a movement that looks like that, and it's through stretching versus something that looks like this and is through compression. Okay, so it's a different type of process. However, some of the topography in Arizona is probably related to convergence due to subduction of an oceanic plate under a continental plate, which was going on back in the Cretaceous all the way to the early Cenozoic. And there is what we call the Laramide too in this part of Arizona, which is, again, a converging type orogenesis or orogenic event. So it's a combination of, again, first convergent stresses and then extension in, let's say, the last 25 million years. And there's a lot of magmatism too in Arizona. So there's a lot of, magmatic rocks at the surface due to.
I was wondering, It's okay. I was wondering about Mount McKinley and whether that is like the Himalayas or like the Andes.
Mount McKinley is more like the Andes because you're looking at a margin where you have an oceanic plate under a continental plate. And so you have convergence, but you don't have collision. So it's more similar to the Andes than the Himalayas.
Are there any examples of large mountains that form from the bottom of the seafloor?
Margins that they form from the bottom?
Large mountains.
Oh, mountains. Oh, yeah. Yeah. In fact, I would say the largest mountains not exposed on the planet are actually underneath the sea surface. So mid-ocean ridges form huge mountains. They're higher than Everest if you're just measuring from the bottom to the top. And that's where basically two plates are pulling apart and new oceanic crust is formed. Those are places where you have a lot of topography being created, but is under sea level. So.
I have a question about Gross Morin in Newfoundland, tablelands. Who said when I visited there that they just popped out of the ground and they just rose up? What are the forces that cause that to happen?
Can you repeat the question, please?
In Gross Morin in Newfoundland, they call them they're tablelands. And they said that at the time when they appeared, they just popped out of the ground. They're raised up. You know anything?
I do not know much about that part of the world, so I wouldn't want to speculate on something that I don't know, but I'll have to look it up.
Right.
So I cannot answer that.
Oh, thank you. This was an excellent lecture. I really enjoyed it. You mentioned your doctoral thesis was on the Alps. Can you discuss some of the topography of that area?
So yeah, the Alps have also extreme topography. The elevation is not as high as the Himalayas, but the topography, I would say, is very extreme. So you go from, let's say, 500 meter to 4,000 meter high, and it's very steep. So the Alps are formed mostly by collision between two continental plates, which is Eurasia, Europe, and Africa. So it's the same basically collision zone that forms the Himalaya. You can actually trace it along strike to the west all the way to the Alps. So that's basically what's forming most of the thick crust that we see in the Alps. Now the modern topography, so the really steep mountains that we see in the Alps, that's mostly related to glaciation, so the last glaciation. So there is a lot of glacial erosion that basically formed that topography, which was really young. So every time you actually see very steep topography, that's usually young, and that's related to glaciation. So it's a combination of processes.
Thanks. Got a real layman's question. Which of these major mountain ranges are growing and which are shrinking?
So what's the question? Some are.
I imagine some of these mountain ranges are still growing because of the tectonic plates colliding, and some are shrinking, like I guess the Appalachian Mountains.
Correct. Yes.
And I was just wondering, in the major mountain ranges that I'd be familiar with, which ones are growing, which ones are shrinking.
Okay, so that's a good question. The Himalayas are still growing because there is still active convergence between India and Asia, so they're actually still forming. The Alps are pretty much dead. If you're looking at the convergence between the plates, there is not much going on right now. So they're actually eventually going to end up in millions of years and tens of millions of years if you stop basically that convergence, like the Appalachians, where not much has been going on for over 200 million years. And so once you stop the tectonic engine and you just put erosion on it, you're going to create a topography similar to the Appalachians. The Andes are also still growing because there is still active subduction on their continental plate. So.
If tectonic movements are a major driver of climate, how significant in reality is human contribution to climate change?
Well, human contribution to climate change is it's well documented by data. So, you know, if you believe in science and if you believe in airplanes flying and gravity, then you believe in climate change. But in terms of the contribution of climates on mountains, I mean, there is definitely a lot of erosion. Climate change obviously is affecting deeply precipitation, like the monsoon and the Asian monsoon. Now, the predictions on how that's going to go, it's not clear, but we're already seeing the effects. And so the Asian monsoon is obviously one of the major players in eroding a lot of the Himalayas foothills, where most of the people in, let's say, Nepal and India live, and Bhutan. And so that's creating a lot of landslides, and so there is a lot of, obviously, big hazards that they're associated with climate change playing an impact on, in this particular case, the Asian monsoon. So, and then of course there is sea level change, which if anyone is living on the East Coast is probably feeling, and so, yeah, that's pretty, the impact is serious.
We can take another question, if anyone has it.
Oh, now you're gonna make me run.
We've discussed a lot about the plates converging on one end. What's happening at the other end? Is it thinning, or are valleys being created? Or can you explain it, please?
Yeah, that's a good question. So if you have something converging and either a plate that is subducting or two plates coming together, you should expect on the opposite end, on the other side, something pulling apart. And that's basically what's going on. Every time you do have a margin that is converging, on the other side you have a margin that is diverging. So you're actually pulling the crust apart, and you're creating, in case of the mid-ocean ridges, you're creating new oceanic crusts. So the whole system is connected in a way that obviously you have to basically balance all these different forces. And so every time you have something going down, you have something coming apart and probably pushing that plate going down. In fact, that's one of the major models of plate tectonics, is that slabs actually get pushed by ridges pulling apart. So,
would you mind answering how you got into this field?
I always loved science. I always wanted to be a scientist since I was little, and then as I grew up, I fell in love with mountains. I grew up in northern Italy, where mountains are sort of part of the backyard, and so geology, just because of that, because of mountains, because of the beauty of mountains, really, not because of a scientific question, because obviously when you're 16, you don't really know. But I was lucky enough to keep that love that continues, so that's how I got into it.
I'd like to applaud Barbara and this audience for cramming in a semester plus worth of geology, geosciences. Let's give her a round of applause. I would also encourage you, if you were compelled and want to reflect on tonight's talk, it will be available on video on the YouTube channel for the DesertView Performing Arts Center. It's available, and then we also upload it on the College of Science Science Cafe website, which is in your brochure. I do also want to just announce that next month's talk, and again, it's Tuesday, December 5th, not on a Thursday. It's going to be by Dr. Jess Tierney. It's the Earth's climate trajectory, past, present, and the future, and that will be. We'll end the year with that talk, and then we'll return in the spring with we have 3 men that will give talks in the spring, and we'll be sure to have that brochure ready for you, etc. But I would like, we've had Barbara talking for over an hour, and so we want to give her a break. But if you do have some burning questions, she's agreed to stay over for a little while. By all means, please fill out the evaluation so we can give her great feedback. And thank you for the evening. And I would also just like to say, hope you have a safe and meaningful Veterans Weekend. And for all our veterans, thank you, sir, for your service.